Okay, I think people are joining in, so I would like to start with the afternoon session. So, as I told this morning, this afternoon we will first start with a first session basically on the analytics. So, all of the presentations you will see in the analytics, they will also be done when you come here in the training program in Belgium. So as a first one of the analytical sessions, Hendrik van de Wegen, who is an organic scientist, will tell you everything about the analysis of polycyclic aromatic hydrocarbons in soil samples. So Hendrik, everything is translated simultaneously, so please speak and articulate very well and take a break once in a while. And after a certain chapter, you can stop. Then we will answer or see what the questions are. I will follow the chat so you can fully concentrate on your presentation. And then for the rest, I would wish you good luck and please, the floor is yours.
Okay, thank you, Christophe. So my name is Hendrik van de Wegen. I'm a researcher at FAO in organic chemistry. And one of the things that I am involved in is the development of analytical methods for environmental samples. For instance, polyaromatics in soil samples. In this presentation, I will deal with the different aspects of the method, starting with the scope and the principle of the method. We will also deal with the pre-treatment of soil samples. That is everything that comes before we have a subsample for analysis. So conservation of samples, homogenization of samples, and subsampling. Then we will cover the extraction and the addition of internal standards, the cleanup of the extract, and the measurement with GCMS. I will also talk about the calibration of the instrument, over the standards, about the standard solutions, how we do the calculations and the reporting, and also important, the quality control and the safety involved with this analysis, safety issues. So let's start with the scope of the method. This method is suited for solid matrices. So soil, of course, but also sediment and solid waste. For sediment and solid waste, some additional sample preparation can be necessary. So this is in fact outside of the scope of this presentation. I will limit the presentation to the analysis of soil. The components that are analyzed are the so-called 16 EPA, polycyclic aromatic hydrocarbons. These are the, let's say, the most important PAHs that are formed during combustion processes, like fire or explosions. Why are these so important? Why do we measure this in soil? Well, these 16 pH are hazardous substances. For instance, benzoapyrene is proven carcinogenic, and the other 15 are probably or possibly carcinogenic. Here in this drawing, you can see how they are formed by combustion. So it can, like a barbecue or a cigarette smoke, or the exhaust of cars, or exhaust of industry emissions. Where you have combustion processes, the polyaromatics are formed. They are deposited on soil. They can also be transferred by rain to the groundwater. But more important, they can be taken up by plants. And when they are taken up by plants, they can come into the food chain. And when they are in the food chain, they can have health effects, negative health effects. So that is why we have to monitor these components in soil. In the Flemish legislation, we have limits for these components. Excuse me, because it's in Dutch, but I think everybody can see what I mean. In the first column, you can see the remediation values. That means if we have a polluted soil and we do a remediation, Then at the end of the remediation, the concentrations have to be lower than the values here in the first column. If the values are lower than the second column, then we can use the soil freely. So you see the most, for benzoapyrene, we have the lowest limit, 0.3, because it's the carcinogenic one. Let's talk now about the pre-treatment of soil samples. That is before we do the subsampling for analysis. The recipients should always be glass or plastic. So not metal or paper, so glass or plastic. The recipients should always be filled completely without minimum air volume. That is because naphthalene, one of the pHs, is relatively volatile. So it's important that we fill it completely without a lot of air above the soil. We do not add conservation agents, and the conservation time for the polyaromatics depend on the conservation conditions. If we put the samples in the fridge, so that means cooled to 3 ± 2 degrees, in a closed recipient, in the dark, we can keep the samples for 2 weeks. Also, if we mix them with chemical drying agent, something we will see later in this presentation, we can keep the mixture for 2 weeks. If we put the samples in a deep freezer, -18 degrees Celsius, in the dark and in a closed recipient, the samples can be conserved for 6 months before we do the extraction, maximum 6 months. So what do we do next when the sample arrives in the laboratory? First, we spread out the sample and we discard all the artifacts. I have here a list of artifacts like concrete rubble, crushed stone, asphalt rubble. So everything that has nothing to do with soil, artifacts. You see tiles, ceramics, artificial slates, but also concrete, expanded clay, plastic, plaster, roofing, bits of rubber, insulation materials, and also metal pieces like bolts, nuts, and scraps, pieces of wood, treated or untreated, asbestos suspected material, paper, cord, textile. So everything that is not soil related, we remove it. After that, we visually inspect the sample on particles larger than 4 mm. If particles larger than 4 mm are present, we sieve the sample over a 4 mm sieve and we discard the sieve residue. So we only keep the pass-through that is smaller than 4 mm. Then we will homogenize this sieve pass-through. There are different ways we can do the homogenization. Most used is quartering or riffling. For riffling, there are two instruments used. That is the stationary riffler and the rotating or the spinning riffler. So what is quartering? Quartering means that you have here a kind of device where you put, for instance, 1 kilogram of sample on this device. The sample is divided on the 4 quarters, and we only take the first, the first and the fourth quarter. The second and the third we eliminate, we discard. We only use these 2. We mix them together, and again, we divide them over the 4 parts. Again, we take only the first and the fourth part. We make a new sample with these 2, and we do again the quartering, and so on. So in fact, we have a sample reduction until we have like 4 times, and then we have subsamples. If we start with 1,000 grams, after 4 times, we have approximately 62 grams of subsample that is ready for analysis. So instead of this manual process, you can also use special instruments like this one, the stationary riffler, where the soil is divided between slits, or automatic instruments like the rotating or the spinning riffler. So all these instruments, the purpose is to homogenize the sample. Once the sample is homogenized, we come to the subsampling. So we take an analysis portion. For this, we mix the homogenized sieve passage with the spatula, and we manually take out an analysis portion, for instance, 5 grams. If the sieve passage contains particles larger than 1 millimeter, then we have to take at least 6 gram samples and homogenize. The analysis subsample is then extracted. Now, the extraction of the soil samples, there are different steps in this process. The first is the chemical drying of the subsample, because soil normally is wet. It has like a dry matter of 80% in general, so we have 20% of water. This water can make it difficult for the extraction. So we have to bind the water with the chemical drying agent. After the drying of the sample, we will add the internal standards. I will come back to this later more in detail. Then we do the Soxhlet extraction and we concentrate the extract. To the right, you can see a Soxhlet apparatus. I will come more in detail in a later slide on this. But the principle of the extraction is a warm extraction. So instead of Soxhlet, we can also use other techniques with warm extraction. For instance, pressurized liquid extraction. This is an instrument that can be purchased. It's a very fast instrument. In 30 minutes, you can have your sample, but it has also some drawbacks like clogging of the tubes and solvent leaks. So at FAO, we do the extraction always with Soxhlet. So these are the different steps of the extraction. First, the drying of the sample. We start with the homogenized subsample, and we mix it in a mortar with the same quantity of drying agent. In this case, sodium sulfate, water-free. At FAO, we take generally 10 grams of sample and 10 grams of sodium sulfate anhydrous. After mixing, you get a dry powder like this. And that is the powder we are going to extract. So we weigh a portion of this dried soil in a Soxhlet thimble. Here you can see a thimble that is used in the Soxhlet apparatus. So we weigh the sample in the thimble and we top it off with glass wool and we add a known quantity of the internal standards. The internal standards are isotope labeled PAH. In our case, deuterated PAH. At least 5 isotope labeled pH are used, representative of the boiling range. At FAO, we add all 16 PAH labeled, so deuterated pH, and we use a solution of 5 microgram per milliliter, and we add 150 microliter, so that in the final extract of 1 milliliter, we will have approximately 750 nanogram of each internal standard. Of course, you can do differently. It depends also on the sensitivity of your instrument and of how much of the extract is injected in the gas chromatograph. Here I have a picture of a Soxhlet extraction. You can see here a blank, and this is a sample. What is the principle of the Soxhlet extraction? Well, the solvent is in the round bottom flask. It is heated. The vapors are going up, come in the condenser. Here they condense. It's cooled with water, and the condensed solvent drips onto the sample. When this chamber is full, it goes back into the boiling flask, and the process starts again. So it's several extraction cycles that are performed one after the other, each time with fresh solvent. How do we set up a Soxhlet? Well, first we rinse it. We rinse the Soxhlet apparatus, including the thimble and the glass wool by refluxing it with acetone hexane 50-50 for at least half an hour. Then we empty the setup, we dry the thimble and the glass wool. Alternatively, we can also clean the Soxted glassware by heating overnight at 450 degrees Celsius. That will also remove all the PAH that are present. So the thimble, the sample with the internal standards, is placed in the apparatus. The round bottom flask is filled with acetone hexane, in our case 90 ml, and we heat it for 16 hours. So the extraction takes place overnight during 16 hours. After that, we will evaporate the solvent. So we concentrate the extract to 1 milliliter using a gentle stream of nitrogen. And during concentration, the solvent is exchanged to N-hexane. Here I have another example of a Soxted extraction where you can see a blank and a sample to the right, and you see the sample is much more colored because you have pH and also other components that are extracted from the soil. Much of these components can interfere with the measurement. That is why we also have to do a cleanup. I will go more in detail right away, but this is in fact a picture of a cleanup where you can see that the sample, a lot of these interferences are trapped on the column and the final extract is cleaned. I don't know if there are already questions now about the extraction before I go to the cleanup.
I have a look in the chat, Hendrik, but there are no questions to that point. I'll wait just a moment to see. But I think with the pictures and your explanation, everything was clear, Hendrik. So I propose you can continue from here on.
Okay. So I proceed with the cleanup of the extracts. When you have very soil that is not very polluted, then you can skip the cleanup. But in general, polluted soil, like soil that is polluted by explosions or by fire, there is a cleanup necessary to remove all the interferences. So as you can see, the cleanup, we use a glass column with a diameter of 1 centimeter. And we fill it with 1 gram alumina, activated overnight at 450 degrees and stored at 105 degrees. Then we fill with 3 gram silica, stored at 105. And we top it with 1 centimeter of sodium sulfate water-free, stored at 105. The column is then conditioned with 20 ml of hexane. So that is to rinse the alumina and the silica, and we discard the eluent. Next is the sample cleanup. Once the column is conditioned, we bring the extract in N-hexane on top of the column, and we let it sink in the column. We rinse the recipient with 2 ml of hexane, and we bring this hexane on the column, and we also let it sink in the silica. We repeat this a few times, 4 times, and we discard the eluate from the column because it only contains interferences. Then we elute the interferences again with 2 ml of N-hexane, and we discard the eluate. At that moment, we can start to elute the PAH. So we place a collect tube under the column, and we elute the pH with 20 ml of a mixture of hexane and dichloromethane 50-50 volume. These 20 milliliter eluate, they contain the pH. We evaporate the eluate to 1 ml, again, using a gentle stream of nitrogen, and we add the injection standard. The injection standard is used to calculate the recovery of the internal standards. Sometimes samples can contain sulfur. You can see that visually when you see in the extract that there are small yellow crystals. Then we have sulfur. The problem with sulfur is that it can create a big hump in the chromatogram. I will show an example. Here, you can see a big hump in a chromatogram. And after the cleanup, the hump is gone. So how do we do that? Well, we let the sulfur react with copper. So just before use, we activate the copper. This can be powder or plates. We soak it a few minutes in nitric acid, 1 normal. Then we rinse the powder or the plates with water. We rinse it with acetone and we let it dry. Then we add a few copper plates to the final extract and we shake. So when there is sulfur present, you will see that the copper becomes black because of the reaction with sulfur. And we repeat until the coloration stops. That means that all the sulfur is bound to the copper. And at the end, we filter the extract on a 0.4 micrometer filter. Here you can see an example of how the copper plates or the copper powder looks. So this was the cleanup. I don't know if there are questions about cleanup before I go further with the measurement.
No. Is this a standard practice? Or only when you see visually the crystals?
Yes, only when you see visually the crystals. And normally in soil, normal soil, it will not be necessary. But that will also depend on the kind of explosive that have been used. If this explosive contains sulfur, then it's possible that you have sulfur in your extract.
Yeah.
But in general, the samples we did here, the FAO samples, we did not use the copper cleanup. It was not necessary.
Okay. Yeah. Thank you. I don't see any other questions, Hendrik, so please go ahead.
Okay. So I continue with the measurement of the extract. The pHs are analyzed with gas chromatography coupled to a mass spectrometric detector, GCMS. This is a schematic view of a GCMS where you have here the samples. The samples are injected in the injector of the gas chromatograph and are separated, the pHs are separated on a GC column. After separations, the components come into the MS via the interface. They are ionized in the ion source, and then the mass selection happens by a quadrupole. Finally, we have the detector and the data system. This is an example of a GCMS that we have in the laboratory at FITO. So here you can see there are no samples here, but this is the sample tray. This is in fact a robot that takes the samples and does the injection. Here we have the injector. Inside we have the column. And at the left, we have the mass spectrometric detector. Maybe a little bit explanation about chromatographic separation. What happens in the chromatographic column? Well, the PAH, you see here 3 different pH. They all have different affinity for the column phase. For instance, the yellow one has more affinity and will stick longer to the phase than the blue one. And after a certain time, we have helium flowing through the column, so the components are also transported by the helium. The yellow one will elute later than the blue one, because the blue one is less retained. That's the principle of chromatographic separation. At the end of the column, where you have the detector, you will first see the blue one, then you will see the red one, and then you will see the yellow one. So they are separated in time. In general, we inject 1 microliter of the extract in splitless mode. That means that the complete 1 microliter comes onto the column. Alternatively, you can also use an on-column injector or a programmed temperature vaporizer, a so-called PTV, but I will not go in detail about this. This is technique. It depends on the instrument that is available in your laboratory. For separation, the capillary column, we use an apolary phase, like 5% phenylmethylpolysiloxane, a so-called DB5 column, 30 meter long, 0.25 millimeter internal diameter and 0.25 micrometer phase thickness. The drawback of this column is that benzo A and benzo B and K fluorantane are not separated. We can separate these components on a 14% cyanopropyl phenyl column with the same dimensions, but then we have a coelution of chrysane and triphenylane. So neither column is perfect, but these are the columns that we generally use. The detector, the mass spectrometer, is operated in the selected ion monitoring. That means that only selected ions are detected. We don't take the whole spectrum, the whole mass spectrum of the component, but only very specific ions. I will show the ions in the next slide. And then the peak identification is based on the retention time in the chromatogram. We can maximum deviate 5 seconds from the retention time of the same pH in the calibration standard. Here you see the principle of selected ion monitoring. This is the chromatogram. You see the time goes from left to right. So this peak compound A is the first one eluting. Then we have compound B, and then we have compound C. With our detector, we take a mass spectrum, and we see the different masses that are characteristic for this compound. In SIM, that is what we use, SIM, selected ion monitoring, we only look at the selective ion. So we don't record the others because there is no signal. And if we only record the ions that are characteristic for this compound, then we can have more sensitivity. So these are the ions that are recorded. Like for naphthalene, for instance, we have mass 128. For acinaphthalene, 152, and so on. I also put the corresponding internal standard in the third column here. Here you can see that naphthalene, acinaphthalene, and acinaphtane are calculated with this internal standard, deuterated naphthalene. Fluorine, phenanthrene, and anthracene are calculated with this internal standard, ditin anthracene, and so on. Also, the deuterated compounds have their specific masses. Here you have the internal standards, the deuterated compounds, and they have masses that are higher than the native compound. Remember, naphthalene was 128. D8 naphthalene is 136, 8 masses higher, because we have deuterium instead of hydrogen. To calculate the recovery of the internal standards, we use injection standards. We have 2 injection standards, one methylnaphthalene and perilene deuterated. And here you can see also that the first components are calculated with the 18 methylnaphthalene, and these internal standards here are calculated with D12 perilene. This is an example of a chromatogram. This is the total ion chromatogram where we have summed all the ions. And this is a selective ion chromatogram. For instance, this is the ion that is typical for fluorine with mass 166. You can see clearly popping the fluorine out of the chromatogram, because all the other components don't have this specific mass, so they don't give a signal. The same here for fluorantane and pyrene. You see these 2 components. You can see them clearly here when we look at the selective ion. Here we have the same fluorantane and pyrene, the 2 peaks on ion 202. And here, this is the ion chromatogram of the deuterated internal standards, fluorantane and pyrene. These are D10, so the mass is 10 higher than the native. But they elute at the same retention time, as you can see, of approximately the same retention time. Are there questions about the measurement and the GCMS, or is everybody knows how it works?
Can you maybe, the total ion chromatogram, Hendrik, is then summing up all the counts of what he measures? Is that correct?
Yes, of all the masses that we have here in this list. So all the masses here, all these masses are measured. And so the total ion chromatogram here is the sum of all these masses. So you see all the different pH, but it's only when you look at the specific ion that you can pop out the specific component. You have to see it as different wavelengths. Specific for.
And then basically the retention time is the time, so the x-axis that gives you an idea, and the mass, so those two you use to select your compound.
Yes, for instance, if you have, this is the calibration standard, and you see we have fluorine at 10.29 minutes, and we have the specific signal on the specific ion. If we have the same in the sample, then we know this peak is fluorine.
And I noticed that you allow a 5-second time interval on the retention time.
Yes, 5 seconds is allowed.
So if the peak is further away than 5 seconds of this peak, this would mean that, there is quality control has to be done, or you have to look further into that.
Then it is not identified as fluorine.
Okay. All right. I don't see any other questions on this part. So I propose you go on, Hendrik.
Okay, now we come to more to the mathematics, to the calculations. Before we can do calculations, we have to calibrate the instrument. So that means we have to know what is the response of the instrument in function of the concentration. There are several ways to do a calibration. I will discuss the two most used. First, the linear calibration curve. To establish this calibration curve, we inject a series of calibration solutions. Minimum 4 different concentrations, excluding 0, with raising concentrations of pH and constant concentrations of internal standard. And we inject this before the samples. So for each component, we can then put the peak area divided by the peak area of the internal standard. We can plot it against the concentration divided by the concentration of the internal standard. And with regression analysis, we can calculate the equation of the curve. Here we have the equation of the curve, and that gives us the relation between the surface of the peak, the peak area, and the concentration. We determine the linear range of this curve, and within the linear range, the deviation of the points to the curve must be lower than 20%, the so-called residuals. That is something that is usually automatically available in your software. For the lowest point, we allow 25% deviation because the measurement uncertainty is a little bit bigger on these low concentrations. Here you see an example of a curve where on the x-axis you have the concentration divided by the concentration of the internal standard. And on the y-axis you have the area of the component divided by the area of the internal standard. And here we see a linear curve.
Hendrik, could you comment how the peak area is calculated, or how it's done and how you have to do it?
That is done by integration of the peak. That means that the baseline, I don't have a picture of this, but normally this is automatically done in the software. And in general, you don't have to do a lot of corrections. Mostly the baseline is correct in the software, and the peak area is tabulated by the software.
So the software does the integration of all the peaks and attributes a certain peak area to that peak. Okay.
Yes. I don't have an example of this, but I think people who know chromatography know what I mean with peak area. Okay, then we have, instead of the linear curve, we can also calibrate using the relative response factor. There, we use only one calibration solution with a known concentration of native packs and internal standards, and we inject it before and after the samples, with a maximum of 15 samples in between. The relative response factor of a compound is calculated with the peak areas and the concentrations of the component and the internal standard. And this is the formula. So we have the peak area of the component divided by the peak area of the internal standard, multiplied by the concentration of the internal standard, and divided by the concentration of the component. The relative response factor method can only be used if the RRF is constant within 15% in the measurement range. What I mean by this, here you see we have injected 6 different standards, calibration solutions, with concentration ranging from 2.5 to, let's say, 0.1. When we calculate the RRF for a component, I think this one, it can be naphthalene, you can see that for each calibration solution, you get a different RRF, slightly different, but as long as these are within 15%, we can use one of these points to calibrate our analysis. How do we calculate then the result from this calibration? When we use a linear curve, then we have the equation of our curve, and we can fill in the ratio area divided by area internal standard in the sample. And then by this equation, we can calculate concentration divided by concentration internal standard. Then the concentration in the final extract is calculated by multiplying this ratio, concentration divided by concentration internal standard, multiplying with concentration internal standard. And we have the concentration in our extract. Then we have to go from our extract to the sample. That is also a calculation, and that takes into account the concentration in the extract, the volume of the final extract, and the sample weight, corrected for percentile matter. So that is a calculation with the curve. We can do the same with the RRF. We calculate the concentration in the extract using the RRF in this way. So we multiply the area of the peak with the concentration of the internal standard, and we divide by the area of the internal standard multiplied by the relative response factor. And then the concentration of a compound in the sample is calculated from the concentration in the extract using the volume of the final extract and the sample weight, corrected for percentile matter. These are also calculations that can be done automatically in the most of the software. So I will not go further in detail here, because most of the times this is automated. I don't know if there are questions about the calculations and the calibrations before we go to the quality control.
I don't see any question on that, Hendrik. I think indeed it will probably also be more obvious when working with the software and seeing it during, but I think, yeah, calibration or in general, the principles, I guess, are familiar.
The mathematics are a bit theoretical. Huh?
Yeah, but I don't see any questions, Hendrik, so please proceed with the quality control.
Okay, this is very important because we want to have control on the quality of our result. There are different quality controls that we have to apply in the method. I have here a summary. First, we have to see if the sensitivity of the instrument is good. Then we have to look at the procedural blank to see if our reagents or the glassware does not contain polyaromatic hydrocarbons. We also have to calculate the recoveries of the internal standards in the sample. The recovery of the internal standards will tell us something about the cleanup and the extraction. If something went wrong with the extraction, then we will see that we do not recover the internal standards. If something goes wrong with the cleanup, you will also see it on the recovery of the internal standards in the sample. So for each sample, we have to look at the recovery of the internal standards. Then we also have an independent control standard. That is an independent calibration solution. And we also use a control sample or analysis of samples in Duplo. Most of the time we use a control sample, and I will come to this right away. I will start with the control of the sensitivity of the instrument. How do we check it? Well, we use our lowest standard. So the sensitivity of the instrument is checked using the response of the calibration solution with the lowest concentration level. The sensitivity is checked at the beginning and at the end of a measurement series, and it has to be sufficiently low to guarantee the reporting limit. For instance, in our case, for pH, our reporting limit is 1 microgram per kilogram dry matter. The second quality control is a procedural blank. For this, we use blank soil, for instance, blank sand, and we treat it like a sample. So we do the complete drying with sodium sulfate, extraction with Soxlet, cleanup on the silica alumina column, as if it was a sample. We include one blank in each measurement series. If multiple series are analyzed per day, then one procedure blank is sufficient. The chromatogram must be free of interfering peaks that are bigger than 10% of the pH recorded for the sample, with the exception of sample values smaller than 5 times the limit, the reporting limit, for which the interfering peaks may not exceed half the reporting limit. It is a little bit complicated, this phrase, but I will demonstrate it with an example. For instance, if the reporting limit is 1 microgram per kilogram dry matter, and the concentration in the sample is between 1 and 5, say 2 microgram per kilogram dry matter, then the blank concentration must be below 0.5. That is half of the reporting limit. If the concentration is higher than 5, that is 10 times the reporting limit, then the blank concentration cannot be higher than 10% of the concentration. For instance, if the concentration in the sample is 7 microgram per kilogram, then the blank must be lower than 0.7. So the blank value can never exceed 10% or half of the reporting limit. The recovery of the internal standards in the samples, each internal standard has to be recovered between 50% and 130%, except for D8 naphthalene, where we tolerate 40% because it's a more volatile compound. If the recovery of the internal standard is lower than this lower limit, so lower than 50 or 40%, but higher than 20%, then we can still report the result with the remark on the report. If the recovery of the internal standard is lower than 20%, no quantitative result can be reported for the corresponding pHs. An independent control standard is used to control our standards. So in fact, we have to purchase standard material from different suppliers. If some supplier has faulty standards, then it can be detected by using an independent calibration from another manufacturer or another supplier. And we use it to check the calibration standards. Not all the pH have to be present, so we don't need to have all the 16 in this independent control. Sometimes it's difficult to find another supplier for all 16, so 5 pH is sufficient. The independent control standard is measured every 3 measurement series, and the concentrations of each pH in this independent calibration standard must be within 20% of the true concentration. The control sample is very important because it gives us a proof that the whole chain from extraction to measurement was functioning good. A control sample that can be a certified reference material. For soil, for instance, you can purchase CRM 535. That is a reference soil with known concentrations of pH, certified concentrations. If you don't have a certified material, you can also make one yourself by fortifying a soil sample, so adding pH to a soil sample. The control sample is analyzed and the recoveries of the pH are calculated. The recovery is 100 times the calculated concentration divided by the certified or the spike concentration. The acceptable values for recovery for each pack are 70 to 130%. You can also do analysis of duplos. Normally, when you have a control sample, you don't do duplos, so you do one or the other. At least one sample of each measurement series is analyzed 2 times, so in duplo, in independent measurement series. And the results must be within 30%. So if the first result is 10, then the result of the second analysis must be between 7 and 13. I already told that these are hazardous substances, carcinogenic. So,
Hendrik, can
yes,
I just some questions on the quality control, or unless because now you were going to the
yes,
safety?
to the next
Yeah,
topic, yes.
yeah, okay. No, thanks. Just a question. So you were mentioning the recovery of the internal standard has to be within the 50 to 130%. I suppose you correct all your concentrations with the internal standard. Is that
Yes.
correct?
Yes, as you could see in all the formulas, I will go back to the formulas.
Mm-hmm.
We use always the area divided by the area of the internal standard.
Mm-hmm. Okay.
So everything is calculated in relation to the internal standard.
Yes. Okay. Thank you. And then another question. Are there round-robin tests available for the determination of pH in soil?
Yes, if you have a quality control system in the laboratory, you also have to participate in interlaboratory testing. There are for soil, packs in soil, I think, yes, there are some, I think, NME AQA, but I'm not sure, I have to check. But I think it's NME AQA in Australia who is doing an ILT for pH.
Yeah. Okay. And then the question, what are the typical variations you would expect in these kind of interlaboratory trials related to the pKs? And is there a lot of differences between the different compounds?
Well, let's say that in general, these interlaboratory reproducibilities are lower than 30%. Sometimes as good as 8, 9, 10%. And then on the basis of this reproducibility, your Z-score of your laboratory is calculated, and you can see how good you performed in relation to the other laboratories.
Yeah. And is this taking into consideration that different methods may have been used in this round-robin test, or would you say this is when everybody is using more or less the same Soxhlet extraction and determination method?
Now, for international interlaboratory tests, every country has its own methods, so we have different methods. So the reproducibility will be a little bit higher. Then we do interlaboratory testing inside one region or one country, like we do in Belgium. In Flanders, we have a system, Erkenningen, where we where we have once per year, we analyze the same sample, all the laboratories in Belgium, with the same method. And there you have narrower reproducibility.
Yeah. Okay. With narrow, you mean less than 30% or
Yes,
even
then
better?
you have in general 10, 15%. Yes.
Okay. As RSD, so relative standard deviation. Okay. Okay. So just it was to get an idea on what is the expectations of the uncertainty you may expect from these kind of measurements. Okay. I think that was it regarding the quality controls.
Yes.
Yeah.
One important note to end with, and that is that we have to realize that these are hazardous substances, carcinogenic. So we have to minimize exposure to these situations and substances and take measurements to protect our health and safety. So always use safety glasses, a lab coat, and chemical-resistant disposable gloves. These gloves, you throw them away each time you use them, so don't keep them to use again. When you manipulate pH standards or samples or extracts, each time you use the gloves, after use, dispose them. Manipulation of samples as solvents and extracts, or preparation of the standards, dilutions, calibration solutions, always work in a fume hood, or use a point extractor, because these solvents also are not so good for your health, like toluene, hexane. So always work in a fume hood. I think I'm at the end of the presentation. So if there are questions, we didn't have a lot of questions until now. I don't know if that is because everybody knows this analysis very well, or because there were some things maybe not so clear.
Yeah. I see that Nathan has a question. Nathan?
Hi, Hendrik. Thank you for that.
Nathan?
I was just trying to thinking of precautions from a soil sampler point of view. I think you had mentioned that air drying samples, you can get loss of naphthalene. Any other precautions like that as far as sample handling? I guess would be part A. And then part B, I know some types of soils like peat soils or highly organics can cause false positives for some extractable hydrocarbons and stuff like that. Do you see any issues with different types of soils when analyzing pHs or highly organic stuff or so forth? Maybe
well, to begin with your first question, air drying of soil is not advised because you can lose naphthalene. So we don't do it. It's even forbidden in Flanders. If you measure pH, you have to dry it chemically. You cannot dry it in the oven, your soil sample. And the second question was about false positives, interferences that behave as pH. Well, the chance is very low because we have this retention time that has to be correct. We also have the specific ion of the component. But even then, pHs are always detected as a pattern. In general, you will never see 1 pH or 2 pH, but you will always see at least 10 of the 16. So that gives 3 points of guarantee that you're a positive identification. So if you only find 1 pH and a very high concentration, then that is doubtful. In general, you have to find at least a few pH.
Yeah, I know they like to, what's the word I'm looking for? Adsorb onto compounds. So it's one of the issues maybe you get with pHs in water, right? If you have a lot of silt or sediment.
Yes.
But I guess that wouldn't really pertain to soil so much, but leave it out there.
Yes, in water samples, in fact, they are not water soluble, these components, and they stick to the sand and to the floating material.
Before going to the question in the chat group, I would like to continue on this interferences, Hendrik, because it was a very useful tip and trick, I would say, you never see a 1 pH alone. So it's an indication if you would only see one that there is an issue. So you always expect more. What is another kind of tips and trick or related to interferences that could be observed or that you, within your experience, have observed to appear when doing soil analysis?
Well, let's say one of the most important interferences can be mineral oil. So alkanes, alkenes, a big mixture of all kinds. But these are eliminated by the column cleanup, by the silica alumina cleanup. So in fact, normally with soil, you will always have very clear chromatograms like the one I showed, with very nice peaks of polyaromatics. I don't expect problems. Also, the FAO samples were relatively easy to analyze.
Okay, then thank you for that. We got a question from the audience, and it's like, which interface between the chromatograph and the mass spectrometer is best for this analysis?
Well, it's just a heated tube. In fact, I will go back to the instrument. The interface here is just a heating. So here we have the injector. The injector is at 275 degrees typically. Then the column starts at 40 degrees and is heated to 250 or 300 degrees. And one after the other, the pHs are released to the MS. The interface is held, the interface is held at 250 to 300 degrees, so that all the pHs can pass through, because you know the column just passes through a heated interface. This column is going through the interface in the ion source. Here it stops. After the ion source, this blue line is not the column. The column stops here in the ion source. And in the ion source, there is a bombardment of electrons, and the pHs are transformed to ions. Ions that can be accelerated in electric fields and measured in the quadrupole. So the interface is just a heated tube.
Okay, so but then indeed the heated tube ends up at some point where it gets bombarded by ions to get
Yes.
the pH in charged, because indeed you need a charge to be able to separate them in the mass spectrometer.
Yes.
Yeah. You were just referring as well, Hendrik, to this oven program. Is this, of course, to one hand related to the column you use, but is this also like standard? Is it put in a standard what the temperature of the oven program is?
The oven program is not critical. You can have very different oven programs. Normally you start at a lower temperature, and then at a certain degrees per minute, like 10 degrees per minute, you go up to 300 degrees. It's not critical, but anyway, in the SOP, you can find all the details of the parameters in the SOP of the
Yeah, maybe I have to add that because indeed, for all the trainees who will come to Belgium, we have foreseen a SOP, so a standard operating procedure, where the full explanation of what Hendrik just told will be written down in step by step, so that this is indeed the standard operating procedure that you will be using or that will be trained on. But this will be indeed given once you will come here, so the SOPs will be made available.
Yes.
I think Nathan also, out of curiosity, put a question in the chat to see a little bit indeed, because that was also your question, Hendrik. What is which of the participants now have the capacity to analyze pH in Ukraine? I don't see too much of a response. Yes, so it was a question by Sergius. So indeed, yeah, we will also have to see how this will evolve. Let me wait some more seconds to see if some questions are pumping up. And also maybe for the one who posed the question on the interface, if that was a clear answer or not. please feel free to.
Oh yes, thank you.
Okay.
I understand it.
Okay. Yeah, it's the interface here is in fact a transfer line. It's just transferring the components.
Mm-hmm.
There is nothing happening in this interface.
Yeah. Yeah, I see one indeed. There was one positive answer, and the Ukrainian Laboratory of Quality and Safety, they are measuring pH, Hendrik. So just for your knowledge.
Okay.
What about the maintenance of the instrument? Is it something that needs on a regular basis some cleaning of the instrument, or how you deal with that?
There is you need to regularly clean the injector first, because in the injector, as I told you, it's 275 degrees. This in the injector, the pHs are evaporated to the gaseous phase. But also, for instance, if the sample contains heavy material that has a high boiling point, higher than 300 degrees, this will stick into the injector and it will leave a trace. And the next injection, the pH can absorb to these traces of material. So after a certain time, let's say after 100 injections, it's possible that the injector is dirty and that it has to be cleaned. Also, the MS interface, not the interface, but the ion source, can become dirty after a certain time. Normally after, it depends on how many samples, but after a few measurement series, like 10 or 20 measurement series, it's possible that the sensitivity of the MS is lowering. When you see that it is lower, then the ion source need to be cleaned. And this part, in most of the mass spectrometers, you can take the ion source out, and there is normally a video with explanation how to clean it.
You were just mentioning the sensitivity. Is this the first aspect you would see if there is an issue with sensitivity, that you have to clean your instrument?
Yes, that's in general. It's the sensitivity goes down when the instrument is becoming dirty. And when you have a problem with the injector, here you will see it also on the chromatographic peak shape. Normally we have a nice Gaussian shape, but when you have absorption in the injector, you will see tailing peaks, because the pHs are absorbed here on the dirt, and they are released a little bit later, so that you get tailing peaks. So for all these kind of possible problems with GCMS, normally there are tutorials. Each instrument supplier has tutorials to learn you how to detect problems with his instrument.
Mm-hmm. Yes, I think a very important aspect of the method is that you said you add this internal standards. You use the deuterated for the different compounds. Is this a regular practice internationally, and how much are added? Because you say you can at least 5. What is the standard saying about how much and which internal standards you have to use?
Yes, well, it's a practice that is applied everywhere in organic, because in organic we can make use of isotope labeled internal standard. That means that the component has the same structure, but some molecules like hydrogen are replaced by isotopes deuterium. So in fact, the compound is behaving equally as the non-deuterated compound. So if something happens with your analysis, this deuterated compound will behave in the same way, and you can correct for things that happened during cleanup, for instance, by taking into account the recovery of the internal standard. It's a general practice in organic chemistry with mass spectrometry, also with LCMS, not only GCMS.
And these products are widely commercially available, these deuterated, especially for all the PAHs?
Yes, for the PAHs, it's no problem to find the internal standards. It's very, you can find them everywhere. It's only for certain exotic or new components. Sometimes that is difficult to find an isotope labeled, for instance, for the newest PFAS. Every week there are new isotope labeled PFAS on the market, but for pH, that is already 20 years available. That's no problem.
Okay, thank you for all these answers and practical tips and tricks, Hendrik.
Well, the tips and the tricks, I think we will show them when we do here in the laboratory, when we demonstrate, because there is a lot that you cannot tell or show. The secrets of the kitchen. We will show it in the laboratory.
It's good to hear that there are still some secrets, Hendrik. Okay. I think if there are no more questions on the topic, first of all, Hendrik, I would like to thank you once again for the very informative lecture on the determination of pH in soil. As I said earlier, Hendrik and our colleague Diane Bertels will give the training once you will be here in the laboratory, going over all the different steps that you have seen. And of course, by then you can ask all your questions as well. And as Hendrik was saying, he will tell you more secrets as well by then. Then I want to remind you that tomorrow we have another 2 sessions, very interesting sessions, I think. In the morning, it will be on radioactivity. It's more general session again, dealing with contamination of radioactive materials. This is in the morning. It will be done by someone from the Nuclear Research Center. And in the afternoon, we will have a session on energetic materials, which are explosive and explosive residues. It will also be a general module. Later on, it will be the week thereafter. They will also give the specific analytics on how they do it, but tomorrow is the general session. So if everything goes well, we see each other then tomorrow morning again. So I wish you all a nice day and evening, and then we see each other tomorrow. Thank you.
Okay.
Bye.
Bye.
Thank you. Goodbye.
Bye.
Bye bye.
Bye.
Thank you. Goodbye.